Hello, good morning, everyone. My name is Makoto Nagata of Kobe University, Japan, and we will talk about the exploration of a full chip level SCA simulation, side channel attack simulation or side channel analysis simulation. And my co-author is Kazuki. He is my PhD student. And I think I will start with some introductory things, what the background of our research, and then he will present more in detail about the technologies we have so far developed, about the simulation technologies. So outline is here. So why we need the simulation techniques for the hardware security, this is the one part I will talk about. And then the, countermeasure techniques, how that we can apply the circuit techniques, the different types of algorithm or different types of the architecture or circuit level things, how we can do this. And with the simulation techniques that will approve or that will justify why that you use such techniques in the implementation of the cryptographic algorithms. And and so forth. I think the number 3 and number 4 you will be talking about, right? In more detail. Okay, so this is the kind of our position. So I'm kind of the designer. I'm designing circuits, and we are implementing many chips for different applications. And is there any pointer? Okay. Okay, so here that I'm integrated circuit designer, and nowadays the chips always need to be compliant to the different type of the requirements. For instance, one from electromagnetic compatibility. This is the area we are often talking about the safety and the reliability of the issue, these things. Sometimes you may have the electromagnetic waves radiated that may cause something in your system, but chips need to be resilient. Chips need to be tough. So this is the idea why we are talking about the designs for the EMC in the IC chip field. And at the same time, we are considering the hardware security. I think this is the field you are mostly working on, how that the chips can be protected against the different types of the attacks, side channel attacks, or sometimes you need to have the great protection about your privacy data, private data as well. And those the kind of different backgrounds we always need to be considered, even though you are just kind of the circuit designer. Every IC designer needs to know the many different things at this moment or nowadays. So system verification, safety and reliability, security and privacy are all in the backside of our designs. This is my area. So how we can do this? We need to have the many different types of simulation techniques. We have been so far explored or targeted the many different types of simulation techniques like nowadays so-called multi-physics simulation. You just use the simulation techniques for the circuits. At the same time, you will use the circuit techniques for the electromagnetic irradiation or radiation and how those will be interacting with your device or your information systems. Those are kind of different types of the things to be combined together in the single simulation frameworks. This is a multi-physics simulation. I put the blue here in the backside. But if you design a circuit, you need to have the more detailed types of the simulation techniques like transistor level simulators. We're still relying on the SPICE. I think you may know the name of the SPICE. This is the kind of a very basic physical level, transistor level simulation techniques. SPICE is always a key for us to design the actual circuits, practical circuits, but the limitations are there. They can't handle the EM radiations, or they can't handle the interaction with the systems, information systems, and they can't handle the side channel attacks, side channel leakages. So we need to have some bridges. We need to have some connections, theoretically and also practically by using the existing simulation software. So what's the connections? That's the point that we are targeting. So that we are designing CryptoCore. We will use the transistor-level simulation for the detailed the analysis of, I think, mostly for the exploration of the root causes of the problems, like a side channel leakage. How that leakage was coming from the actual circuit device, circuit operations. This is the area we are applying in the transistor-level simulation here. So those two are different, obviously quite different topics, but we need to do things together. in the same or in a single design flow. Okay, so now I want to go more into the details in the technologies. Here is a kind of the chart showing you how the chip will be interacting with the in the surrounding world. The chips, the digital circuit of interest, I think the cryptographic module will be in that area, and that will be supplied by the power converter, like a DC-DC converter or low drop voltage regulators, kind of that will be supplying the chips internally, and those will be connected to the external field through the packages, PCBs, printed circuit boards to this external system level power supply. Why we are talking about the power noise? Because every time the chip's working, some of the logic will be switching and consuming the power. That will be directly coming out to the system level power supply, because the system level power supply always providing the charges, powers to the system. So this flow, the current will flowing from the system level power supply to the PCB package, power converter, and then digital circuit, that will be coming back to the system ground through the BSS channel. So this loop will not be broken, because your circuit needs to be supplied and it needs to be operating under properly supplied situation. So this is the link that will be connecting the operation of the circuits, and that will be the source of the leakage through the power noise about the information in the cryptographic engines. We have many different types of the noise simulation flow, but I will not go into the detail because Kazuki will show you more detailed things. But this is the so-called simulation flow. That we have the three different steps. One is the cell characterization, meaning that your logic design will use the standard cells like a NAND gate, flip-flops, and so forth. That will be characterized in sense of how much power that will be produced or consumed by the operation, all depending on what kind of input bits coming to the cell and what kind of the load capacitance, load resistance your logic will have. All the input side and output side will be determining the size of the power. That will be characterized beforehand. And the full chip PDN modeling means PDN stands for the power delivery network. All the chip will be supplied to the metal wires on the different levels of metals, up to 6 or up to the 12 level of the metal layers. Those will be all captured in the power delivery network modeling. And those two will be combined, and then core level power modeling will happen. This is a dynamic types of the power current modeling. But anyway, that details will be given later on. This is a kind of the high-level sketch of the flow. So what's the status now? This is the chart we created back more than 10 years back, like ISCCC 2010. That we had a chip like here on the left-hand side. Here is a microprocessor from Hitachi company. It's a SH. That core was implemented in the specific technology at that time. I think 65 nanometer nodes or something. Not so the latest one, but it was more than 10 years back. But still, that we have more than less than million, but almost like a million gates in the die. How we can model this power supplies? You have millions of gates that will not be handled by the SPICE. SPICE will be limited for the usage about the 10,000 the devices. Quite a different level of the integration you can handle with the SPICE. So our techniques that was developed with a EDA vendor and power modeling, CPM, chip power model can handle all the power consumptions happening inside in the microprocessor core. But the accuracy was the key. How we can confirm the accuracy of the power models. We had some ways of make an assessment of the simulation techniques with the measurement techniques. In this case, we have an on-chip monitor that can give you the idea of what kind of a voltage variation happening on your power domain, power delivery network. voltage variation is directly caused by the current flowing into the power delivery line. Power delivery line has impedance, and the current, if the current flows through the impedance, that will create voltage variations. That can be measurable. That is measurable by the on-chip monitor, and the results will be compared with the simulation techniques. We have 1, 2, 3, 4 different plots here. We have the 6 different probing points inside the die, and some trends we see. All the trends are almost similar, but the absolute number is different. In the vertical chart, the number is kind of the voltage variation, the size of the voltage variations happening during the operation of the microprocessors. In the case with the quite simplified model, very large number, like 80 millivolt peak to peak. But if we have the off-chip model, meaning that if we increase the model of the assembly, packaging, and PCBs, that will give you the more reduced number of the die, reduced number of the voltage variations. And if we increase the silicon substrate in the model, drastically the results will become closer to the measurements. So the implications from this simulation results are, we always need to consider everything involving in the system level assembly, not just the circuits. You need to have all the circuit constitutions on the die, and also the silicon substrate and the package, as well as the PCBs. It's naturally quite reasonable, but we need a technology to handle all of them in a single simulation model. This is a system-wide simulation, concept. What is the waveforms? The waveforms, measurements, and the simulations are quite comparable. Even for the VDD noise, VDD means a high side, like a 1.5 volt, and for the other side, ground side, 0 volt. The ground is not always 0. There are voltage fluctuating when the circuit's operating. Those can be captured by the simulation, and that can be quite comparable to the measurements, meaning that our simulation models are quite stable and quite accurate. And even though that if we see the chip-wide distributions like this, so the the red area is microprocessor itself, clocked at 50 megahertz, always a high level of the noise, but in the periphery we have some gradient from high area to the low area that can be comparable again to the measurements, so that I think the simulation can capture all the chip level noise models. After the 10 years, we applied the techniques to the simulation in the area of security. In this case, people are not just worrying about the size of the drop. They are talking about what's the interaction or correlations they have within the internal operation of the cryptographic engines. So we can simply apply the techniques to the like an AES chip, and the horizontal number is number of the traces, number of the payloads, and the vertical axis gives you the rank of the guessed key bytes. So I think this is quite you are familiar with this kind of plots. We have the 3 different plots. One is blue, which is the most pessimistic. This is the case for the simulation at the on-chip node of BDD, meaning that inside the chip. And the green one is the onboard connector, and the black one is the silicon measurement. So all the trends are same and mostly same, and the simulation can be a bit pessimistic, but it's good for the designing the AES chips. This is a kind of a system-wide usage model of our simulation techniques to the cryptographic world or the chip. And more, that the core of our simulation is how accurately models power current dynamically consumed by the circuits. That can be straightforwardly connected with EM radiations, because you know that once the current flows through the metallic wire, there are magnetic radiations. And from the far field, you can see the EM, electromagnetic waves. That can be now simulated. It's a kind of the connection of the circuit level simulation, power modeling with the electromagnetic solvers. Now that we can simulate. This is another different type of system-wide analysis. Okay, this could be my my last slide, but this is the transistor level simulations. Now we have a very accurate simulations can be done with the transistor models. Sometimes you can apply that techniques to see what something is wrong with inside your chip. For instance, the Kazuki we mentioned about how that the masking type of the cryptography can leak something. That can be simulated with the transistor level ones. In my case, that this is two different chips. Obviously, from the front side or design layout views, nothing be changed. But once you make some simulations, your power current will be something different between the original one and the so-called falsified one. Very sensitive. So that if the design is intentionally or sometimes suddenly changed due to something, but that can be captured by the transistor level simulation. So this is the way of using the assurance of your designs by using transistor level. Okay, this should be my last slide. So as I mentioned, we have many different types of the simulation techniques. The problem here is how we can use this for their security verification suites. The side channel leakage assessments should be done in a pre-silicon in the design phase. And of course, later on, before the sign-off. Sign-off meaning that your design will be finally be manufactured in the semiconductor companies. Before that, we need to be 100% confirming that your design is okay from the side channel viewpoints. So this is the one thing that how that simulation could help the designer, cryptographic core designers, to do the non-leakage, a very small leakage or negligible leakage in your design. And also the photo injection is another category. We are targeting on how that the injection will be coming to the device and that will be captured in the model, and how that will be finally changed in the bit flips, having the bits flipped in the flip-flops, for instance, and those are another things, and we are quite ongoing on this model, not just for the laser irradiation, but also for the electromagnetic irradiation and even the electrostatic voltage pulsing as well. Those are another topic. And also the falsification-free IC chip product assurance schemes that I showed you in the previous slides. Those can be another topic we are targeting. So those are different topics, but quite important. I think you can understand that those could be quite important for the security designs in the IC chip fields. Okay, the detailed technologies will be given by the Kazuki, please.
Thank you. I'll talk about the ongoing work on the new trials I'm now doing for the side channel analysis, countermeasure, and side channel leakage. And first, I'll talk about the relationship between side channel analysis, countermeasure, and side channel leakage simulation. And after that, I'll detail about the flow for the cryptographic core level simulation and also SOC level simulation. I know you know better than me, but there are two types of side channel leakage countermeasures. One is masking and another one is hiding. Masking tries to remove correlation between power consumption and cryptographic operation, secret informations. It is said that it can provide probable security, so it is the one important way of the countermeasure. And another one is hiding. This tries to decrease the signal-to-noise ratio of the secret information and the total power current or something less than power consumption. It can be the time domain hiding or amplitude domain hiding, but both of them are trying to reduce the signal-to-noise ratio. In masking, there are two types of masking methodology which is tolerance against the side channel analysis, even though glitch is happening inside the IC chip. One is the domain-oriented masking, and another one is threshold implementation. These are said to be probably secure under the assumption that the leakage of each share is independent from each other. However, there are some previous works which shows that implementation can violate the security of masking. At the RT level, the security level is correct and the T value never exceeding 4.5, but somehow after the layout, T value exceeding 4.5, it means it can happen the leakage inside the IC chip. This is because of the coupling between shares or coupling between domains inside the IC chip. However, they didn't find out the reason which makes the leakage. It can be the coupling between the signal wiring or coupling through the power delivery network, but they didn't find the reason, so it's really difficult to find the reason of these leakage caused by the layout and make the countermeasure against it. And another one is hiding. I'll skip the detailed explanation of these equations, but important point is the ratio between the exploitable power consumption and switching noise power consumption. Some hiding methodology tries to increase the switching of the power noise which cannot be exploited by attackers. And also another one tries to decrease the exploitable noise by balancing or something like that. In hiding, signal to noise ratio is important because measurement to disclosure is highly related to the signal to noise ratio as shown in this equation. So what is important here is in hiding, it's really important to estimate signal to noise ratio inside the IC chip. So if we have the countermeasure, how we can validate the tolerance of the side channel analysis countermeasure? One way is making the prototype chip, making the chip using the countermeasure and fabricate it and use the exact measurement. However, as you can imagine, it's really expensive and time consuming. So another way we can do is implementing the same register level explanation inside the FPGA and do the exact measurement. However, the current consumption character is completely different from FPGA and ASIC. So that is the reason why simulation is needed. But the point here is simulation accurate enough or fast enough? So I'll talk about these simulation technologies today. If we don't have the side channel analysis simulation, as I said, I have to do the IC design first, and after that, fabrication is needed, and then we have to do the evaluation at lab. And if we found a vulnerability at the evaluation stage, we have to go back to the IC design stage, and respin is needed. However, if we can have the side channel analysis simulation, we can do the evaluation at the IC design stage and immediately makes the feedback to the IC design. It makes the process shorter and less expensive. And of course, it is needed to evaluate at lab at the last stage, but you can do the respin at this design stage. This is an important point of side channel analysis simulation. Today, I'll talk about two types of side channel analysis simulation. One is cryptographic core level simulation. This is contribute to the detailed analysis of side channel analysis countermeasure. As I said, there are some kind of leakage caused by the layout. I mentioned that there are some reports, some previous works which shows that layout can cause leakage, even though the masking countermeasure is correct at the register transfer level. Cryptographic core level detailed simulation can contribute to analyze this kind of source of the leakage inside the caused by the layout. And another one is system level simulation. In this one, as I said, signal to noise ratio is important for the side channel analysis evaluation. And in these days, the circuit becomes larger and larger. So we have to estimate the exact signal to noise ratio inside the IC chip, including crypto core and other components. So I'll talk about these two simulation technologies. First topic is cryptographic core level simulation. There are many components inside the IC chip in these days, but in this cryptographic core level simulation, I'll focus on only for the cryptographic core was the important component inside the cryptographic core. This can help the designer to explore countermeasure methodology or to validate the effectiveness of countermeasure at design stage. And in this evaluation, simulation accuracy is the most important point. So I'll use SPICE, which is known for its accuracy, and it is relied by the IC chip designer for analog designers or digital designers with high speed, with high frequency. And however, this kind of simulation, side channel analysis simulation, has a problems with false positive or false negatives. First, as I said, designer can evaluate the side channel analysis countermeasure level, security level at the design stage, and they can respin the process and increase the security level at the design stage. However, once false positive happens, they need more countermeasure or additional circuits or something like that, so it can be expensive. And if the false negative happens, designer believes that it's secure and it goes to the next stage, fabrication stage, so it will make the security problem. In this presentation, I will report that SPICE, which is reliable for circuit designers, can cause false positive in simulation-based security verification. This shows the internal algorithm of deciding analysis time step inside the SPICE. Analysis time step is time varying, as shown in this figure. This is for the high efficiency. If the detailed analysis needed, the simulation time is longer and longer. So they want to do the less analysis times, increase the analysis time steps so that they can make the simulation faster and faster. This is the internal algorithm to decide the analysis time steps. So user can control only maximum analysis time step. This is a program in the SPICE simulation for the security evaluation. This is a simple figures with different analysis time step. This one shows the larger analysis time step, and this one shows the final analysis time step. As you can see, if the analysis time step is different, the output from the simulation can be different. This is just an example, but this can be happen inside the IC chip. This difference caused by different analysis time step is small enough for IC designers, such as analog designers, or evaluating the speed of the IC chip, which can be worked. But this small difference can cause false positive in security evaluation, because security evaluation use correlation or something like that. So it's really sensitive. So even though these differences are small enough for circuit designers, this can cause the false positive in security evaluation. I'll show the example of this false positive. I implemented this simple function, and this function is implemented with second order domain oriented masking, and this is implemented with using the CMOS 180 nanometer circuits, and this is the layout. After the layout, I use the SPICE simulation to evaluate the power current inside the IC chip and evaluate the leakage. This is the evaluation result. Blue one shows the simulation with maximum analysis time step 10 picosecond, and green one shows the result with maximum analysis time step 1 picosecond. The only differences of this simulation is the setup for maximum analysis time step. This small difference, this small simulation setup can make false positive or false negative. As you can see, one exceeding 4.5 and another one didn't exceed 4.5. It means one can be the false positive and one can be true and one can be false positive or false negative. And with the detailed evaluation, we found that this is the false positive, and this larger maximum analysis time step can make the false positive. We confirmed the same phenomenon using different power delivery network models, and we confirmed that if we reduce the maximum analysis time step, false positive never happens. And this page shows a discussion for a solution to avoid false positive in SPICE simulation. One way can be using another security evaluation metrics like measurement to disclosure or something like that instead of t-test, because t-test is too sensitive. However, to use the measurement to disclosure, we need more the number of waveforms required is more, and also we need the almost complete cryptographic circuit to evaluate it, because we need a model to evaluate the measurement to disclosure. Another solution can be the changing the power noise simulator. I use the SPICE, but there are some power noise simulator using the number of the logical switching inside the IC chip or something like that. It doesn't need to make the analysis time step, because it just counts the number of the switching inside the IC chip. However, as I said, the accuracy of the simulation of SPICE is really high. So if we want to do the detailed discussion inside the IC chip, what is happening inside the IC chip, SPICE is needed. So my conclusion is that we need the appropriate simulation setup for SPICE simulation. Next, I'll talk about the system level simulation. In the trend toward larger circuit in these days, there are many circuits inside one IC chip. One component can be the cryptographic module, and another one can be memory, processor, something like that. So the circuit size of IC chip became bigger and bigger. So we need to estimate the exact signal to noise ratio or exact power current consumption inside the IC chip, including whole system inside the IC chip. As I said, there are some kind of power noise simulation. One is the toggle count based simulation, and another one is simulation using power library, and the last one is simulation using the SPICE. This is the most accurate one. However, SPICE has a problem. When the circuit size is increasing, SPICE simulation time also increases exponentially. This is just an example. In SPICE simulation, if the circuit size became bigger, simulation times goes longer. So I decided to use simulation using power library. This is the topic I'm talking in this chapter. This is the overview of power noise simulation using power library. First, we'll use power library for each standard cells using SPICE level simulation. I'll show the details of how to make the power library of these standard cells later, but this has a characterization of power consumption inside the standard cells, and this is made using the SPICE simulation, so it's accurate enough. And after that, I conduct logic simulation to estimate the switching inside the IC chip, and with the combination of power library and logical simulation, we can use the power current waveform like this. This is the overview of power library of standard cells. Dynamic current inside the standard cells is calculated using SPICE simulation. When the rising edge or falling edge is happening at the input of the standard cells, power consumption is happening, and the characterization of power consumption is calculated using SPICE simulation to make the library for the standard cells. This power library contains information of PVT corners, process voltage, temperature corners, and also input signal slew rate, and also load capacity. It makes possible to do the accurate evaluation for the system level power noise evaluation. And these power libraries are connected to the power delivery network of the IC chip, system level IC chip. These are the power library of each standard cells, and those power library is connected to the power delivery network model, which consists of resistor, capacitor, and each power net, each metal layer of power delivery network and substrate layer is models as shown here. This is the mass structure of power delivery network, and each point is connected to the standard cells power library model. In using this, we can calculate the power current flowing through the power delivery network at every point you want. This is just an example, but you can place the virtual probe at point 0 and point 1 or something like that, so you can sense the point wherever you want. Once you can get the power current flowing through the power delivery network at each point, you can also estimate the magnetic field of just above the IC chip. This is the image of the simulation. As I said, you can capture the power current waveform at each point of the power delivery network over IC chip. And using these power current information, you can calculate the magnetic field using Biot-Savart law, and you can get the electromagnetic waveforms too. This is how to simulate the near-field electromagnetic fields using the power model simulation. To confirm the accuracy of the simulation, we did the comparison between exact measurement and the simulation. And this is the measurement setup. We placed the electromagnetic coil just above the IC chip as shown here, and we did the measurement for the x-axis and y-axis. This is the setup of the evaluation, and we made the comparison between the simulation and measurement. This shows the result of the simulation heat map for the side channel leakage, and this shows the results for the measurement. As you can see, simulation and measurement has highly correlated each other. You can see that the left part of the IC chip has high leakage, and also the center has the high leakage. And in the BY case, you can see the high correlation too. This is how to do the system level simulation, and we confirm the accuracy of the simulation. I'll conclude with a summary. Side channel analysis simulation is important for designers and also for the researchers of the hardware security, regarding the hardware security kind of things. And one important simulation methodology is cryptographic core level simulation for the detailed analysis of the side channel leakage from cryptographic core. And another one is, in the trend of larger circuit, we have to make the system level simulation too. So these are the simulations we showed, and it is important to use the appropriate setup for the simulation to evaluate the exact leakage from the IC chip. And we can use this core level simulation and SoC level simulations in combination. So this is what now I'm trying to make the methodology. That's it. Thank you for listening.